We're delighted to have today from Haifa, Israel, Dr. Ami Altman is going to be presenting on the latest developments in CT detector technology.
Okay. Just to disclose, I'm a Philips employee, so what I'm going to show is mostly from Philips, but it doesn't limit any generality. I'll start with the I'll cover first conventional state-of-the-art and a little bit future conventional CT detection. I'll talk a little bit as a gateway to spectral CT about a dual-layer detector for spectral CT to enable dual-energy CT with some applications. Examples, and I'll proceed to future hope and dreams of radiologists and physicists about using photon counting detectors for spectral CT, multispectral CT, multi-energy beams, and I'll talk about the advantages, opportunities, and some risks. A little bit on CT, if people are mostly from radiography here. So CT today has 2D detection arrays, and scanning is done helically, mostly helically still. So this is, I'm sorry. The movie doesn't work. I don't know why. Here. So this is a 2D wedge geometry of data acquisition in modern multi-slice CT. So multi-slice CT is almost like what you call cone beam CT, but in a wedge configuration. And you expect to get something very, very like this, isotropic resolution, high resolution, isotropic resolution, volume images. And this is how it is realized in a practical CT. You can see the detection system, the source, the collimator, the collimator, the beam collimator, shaping collimator, and the generators. You still see this? Oh, we lose. I lost this. Okay, I'm sorry. I'll proceed. I lost the arrow in.
Let's see, where is it?
I don't see that. How I work it out? Maybe this way. I see. It's okay. Okay. So the basic detector, the basic pixel, CT is using pixelated detectors, both on the photodiode and on the scintillators. And the basic pixel is an indirect converter. Scintillator converts to light, like in radiography, and then you read it out with the photodiode, unbiased photodiode, and it goes to a current integration from the photodiode at a certain specific sampling time, and this is going through A to D, and the requirements are very tough from this kind of readouts and detectors. All the pixels are read in parallel, such that you can read about 10,000 frames per second. Each frame is about 120 in large coverage system, 8 centimeters and above. 8 centimeter coverage in the ISO center, you get lots of pixels, 120,000. Not so much as in radiography, but not so many, but still a lot. The readout is current integrating readout. Electronic noise should be, RMS electronic noise should be better than 3 picoamperes, because you have in a fast rotating CT, you have integration period sampling times that are very short as 100 microseconds. So you need low noise. I'll talk about the noise. We require very low afterglow in the scintillators, about 20 ppm after half a second, and 200 ppm after 3 milliseconds. And this is, or even better, with shortening sampling times and the faster rotation times that are in the market, that are close to 1/4 of a second per rotation. Scattering has to be rejected very well, especially in large area arrays, large coverage arrays. Scattering to primary ratio should not reach more than 5%. And the photodiode has to be with very high responsivity of about 0.35 ampere per watt of light inside. This is more than double of conventional CMOS photodiode. So this is why bulk silicon photodiodes are used in CT. And the dynamic range, unlike in radiography, where dynamic range is 12 bit, 14 bits, this here we are talking about 20 bits. 20 bits, and stopping power is almost 100%. So detection efficiency of the scintillators, the scintillator stops about 98% of 120 kVp spectrum. So I'll go back. So this is in the left side. You can see a pixelated photodiode, front illuminated photodiode that has been used until recently, until a few years ago, still 2005, and still there are vendors that are using front illuminated photodiodes. They limit the coverage along the body, the Z coverage, because you cannot fill the active area with the conducting line and lose diode efficiency. So many of the, at least three vendors moved to a back illuminated diode, where the diode is flip chipped almost directly to the electronics, or very close to the electronics. And in order to avoid crosstalk, these back illuminated diodes are very thin, about between 100 and 150 microns. I'll proceed. As I've talked, as I've told before, scintillators are used to convert X-ray to light. The most used scintillator in in CT is the gadolinium oxysulfate, but it's the doping is different than the Gauss screens that you know from radiography, in order to avoid large afterglow. So protazinium and cerium are used in different balances, and the light yield, intrinsic light yield, is about 40,000 photons per MeV. Recent years, GE has introduced garnet scintillators, probably lutetium-based garnet scintillators, which are fast and has comparable light yield to Gauss. There are other garnets in the market which are under investigation by many vendors and many universities. One of the most promising is the GGIG, lutetium GGIG garnet, which has a potential for more light. It's more transparent than the other garnets and the Gauss, and in few years we might see it in the market. GE used to use also the highlight scintillator, which is yttrium gadolinium oxide. I'm sorry. And zinc selenide was also recently used in CT, although its stopping power is low. It's made of relatively low atomic number elements, but it has very high light yield, and it was used by Philips, at least for their prototype of a dual-layer detector for dual-energy CT. I will go and skip the equation and go on. The next improvement in the last few years was going from module-based detection to tile-based detection. If you succeed in making four-side buttable tiles, you can build any detection system for any kind of CT you wish, and you can reduce the cost of production because everything is modular. And the first to introduce tileable detection system was Philips, but today Siemens is also using small tiles detectors, and probably others too. Here you see such a tile, which is 16 by 16 pixel, has 16 by 16 pixels. You can see the back illuminated diode, very thin diode on a substrate, with together attached to it with a readout ASIC, such that the long lines that we have here leading the signal to the readout ASIC are much shorter or are not there, so you don't have you save on noise, pickup noise, and simplify your assembly. And this is together with the scintillator attached to it, and this is together with the two-dimensional anti-scatter grid. Here you can see one module of such tiles, 8 modules to cover 8 centimeters, 80 millimeters at the isocenter for ICT 256, a premium scanner, Philips scanner, and here you can see it on the full array, full DAS array, and you can see that it's not a cylindrical geometry but spherical geometry in order to enable a single type of two-dimensional anti-scatter grid that from each point it has the same focusing element to the focal spot. And here you see it pictured in reality. A little bit on scattering. We need scattering rejection in very important in CT detectors, since in the whole tomography process, computed tomography process that transforms projections to slices, assumes line integrals that include only purely transmitted radiation. If you have non-purely transmitted radiation, you get non-linear elements in the line integral, and the whole tomography process, which is a linear process, creates artifacts from them. You get cupping artifacts. You can see here cupping artifacts from this is in a system that has only 8% or 9% scatter to primary ratio, and this is in a system with a two-dimensional anti-scatter grid where the scattering SPR is less than 5%. You can see that even in the larger opening, you don't see the artifacts and the cupping. Here you see some trials to correct. There are trials by all vendors to correct for the anti-scatter, the scattering artifact, the scattering artifacts. You can correct it, but you cannot avoid the noise that it creates. So by correcting the artifact, you increase the noise of the system, and so you pay a price for this. A little bit on figure of merits for detectors. Figure of merits of detector are MTF, DQE, especially MTF and DQE. I don't want to teach DQE theory. There is no standard, unlike ICE standard for radiography. There is no standard and no requirement for standard for DQE in CT. In CT, it's more problematic. But there are recently some trials to do some measurements and calculations of DQE in CT. Here you can see this is taken from Philips' paper in SPIE in 2008 or something like this by Randy Luta and et al. And DQE has the conventional definition, and approximately it can be approximated in measurement by this, because MTF can be measured, and at least in zero frequency, and the NPS is also measurable. So the noise power spectrum, and I'm sorry. and this can be done, but and you can see that in CT the lower you go with the dose, at least in zero frequency, if you look, the lower you go with the dose, the DQE is lower, is very low. So current integration systems, like detection systems, like in CT, together with the scintillator, which contributes a lot to the DQE by the swank error, the swank noise. Current integrating detectors are characterized by low DQE at low dose and high DQE going up to 80% at high at zero frequency, at high dose, and this is very important, because in photon counting it's the opposite. We will see. In photon counting, the DQE at low dose is very high. It's close to 100%, and it reduces with high rate. So they are. It's very important to when you analyze the requirements for a system, you have to take it in account. The total detection efficiency should take also geometrical detection efficiency, which is the ratio of the active area of the pixel relative to ratio to the whole pixel area, that includes also the reflectors around it. And so the total detection efficiency is obtained by multiplying the DQE by the geometry count. Well, another issue with such detectors, CT detectors, is a crosstalk. There is some optical crosstalk between through the reflectors. The reflectors are not fully reflecting. They are about 95% reflecting, and they can, especially if you make them thinner in order to reduce the size of the pixel and keep the same geometrical efficiency, you get some optical crosstalk, and also through the optical glue between the scintillator and the photodiode. And you can see that this is a profile of a pencil beam on a pixel, and you can see that it's not a square beam, but you have shoulders. Even in our improved tile, you have some shoulders, and the shoulders, the shoulders reduce they affect the MTF, they reduce the MTF, and there are ways to deconvolve the crosstalk and correct the crosstalk. There is a paper by Ras Karmi and myself already in the NSS, IEEE NSS in 2004, showing how to correct this, and how to correct this in the same manner, with the same deconvolution type, also afterglow. Although we don't suffer from afterglow, we succeeded in doing it, and increasing the MTF at 50% by 1 line per centimeter, which is very significant in CT. So these are in CT. We have to take in account also electronic noise in CT, because we read both the radiation signal and the electronic noise. This is why we require the electronic noise to be very, very low. And this is different in photon counting. one of the hopes is to get a noise, no electronic noise image in photon counting. So you can see here the photodiode current and the radiation signal in terms of number of photons per unit time, and the noise, the total noise, and the electronic noise, and you can see this is on a log linear scale as a function of the absorbing path up to 50 centimeters. And you can see that the current can go, the current that at low MAS, this is for a low milliampere, low tube current. So it goes here from 200 milliamperes to 30 milliamperes. So at low milliamps, even at medium tube current, you can go at when the absorption path, water absorption path, is very high. You can go to signal, radiation signal, or current that is not more than a few picoamperes. So it's very comparable to the noise, and you can see in the noise where the noise bends here in this region that here we can expect some troubles by getting electronic noise to become too dominant in the image itself. So the image values are not reliable anymore, and you can get also some artifacts because the electronics doesn't carry with this only noise, it carries also non-linear effects and some instability of the offsets that most of these kind of electronics have. And you can see partial rings. This is a 50 centimeter water cylinder scanned with only 70 MAS, and such a large absorber, it's not enough, 120 kilovolts, and you can see you can see this is an old system with relatively high electronic noise. We don't have, and nobody has such noise anymore, but even today, this may limit the capability to go very low in dose using the new reconstruction schemes of based on iterative reconstruction. So it may limit because you encounter the low dose artifacts coming from the electronics. Okay, I'm going now to a gateway to photon counting and spectral CT, starting with a trial by already started by Philips at 2004. I gave a talk in RSNA 2004 already about this dual layer, and since then we have had several systems like this as research systems, not a commercial product, but we did lots of work on them with them, and this comprises of 2 layers of scintillators, one light element scintillator, zinc selenide, and the lower one, the bottom one, is a conventional gauze, and instead of reading it from the bottom, we read it with a very thin photodiode from the side. So it looks like this, the array, and the photodiode has to be protected from direct radiation interaction by 1 millimeter of tungsten. You can see even a real tile that we have built for this. So you can see a tile with a two-dimensional two-dimensional two-layers arrays or sticks with 2 layers of different types of scintillators, and this is how it looks in reality. I'll show a little bit on this. I'm sorry. So I'll show it in image domain representation, although our analysis nowadays is mostly projection domain analysis in the reconstruction, but it's better seen, demonstrated if you take each pixel and put it in a scatter plot of the low energy Hounsfield units against the high energy Hounsfield units, you get a scatter plot where each material or element appears along a straight line with the higher densities or concentration far from the origin, where the origin is water. So it's a relative density to density relative to water, and you can see the you can see iodine and calcium lines, and you can see analysis like this between bones and here and iodine in blood vessels and in the heart. You can see the iodine contrast, and the soft tissue is well separated. Also in this, you can see the soft tissue line here, and you can and of course fat can be separated easily. So this is the way you can see it, and I don't want to go through this. There are other dual energy systems, commercial ones. Siemens has a dual source, GE has a KVP switching. They have their advantages and disadvantages. And this is sorted here. I don't want to go through it, but I would like to show at least some of the distinct applications that we can get. I'm sorry. We can see here applications like gout disease detection, because it's very easy to separate or analyze the urea, the crystallized urea in the joints. We can achieve preparation-less CT colonography without preparing significantly the patient before. You can see detection of pulmonary embolism very easily. Iodine maps can give us a tumor lesion. I'm sorry. Lesion analysis here and here. Here is lesion analysis. And lesion distribution of contrast agent in tumors that can give a quantitative distribution, can give you in different phases some indication on the tumor response to treatment. Analysis of soft plaque, analysis of lipid content in soft plaque, and qualifying the soft plaque according to the risk, its risk and vulnerability. Cardiac myocardium perfusion, kidney stone analysis, and so on. With the creation with the creation of monochromatic images, we can reduce metal artifacts, and in addition to all, we can create maps of a effective atomic number of material, and this is very useful in increasing soft tissue resolution. So this is, I'm sorry, this is done. Here you can see some more monochromatic images from 45 keV monochromatic image, where you see lots of contrast enhancement, up to 200 keV, where the enhancement is almost zero, but you can reduce metal artifacts in this kind of images. So you can manipulate between two images to create an image without metal artifact. It's much better than any metal artifact correction. I would like to proceed. Here you can see a typical screen of our spectral console. Here you can see a monochromatic image with the possibility with the ruler to go from 40 to 200 keV. Here you can see automatically it finds the maximum CNR monochromatic image that may be the best to see the Hounsfield units and the low contrast resolution. I'm sorry. And of course you can see an analysis of the atomic number maps that before that nobody could see something like this. Okay, so it seems to, at least to CT radiologists, exciting, and pushing CT towards not, I wouldn't say molecular imaging, but imaging some molecular processes. And it looks like a gateway to more energies, to real multispectral CT, and real multispectral CT can be done only with the photon counting systems. So I'm going to photon counting detectors. Photon counting detectors are very different from the conventional detector. From the conventional detector, in the conventional detector, you first convert to light. Here, you have a direct converter sitting directly on the electronic ASIC, readout ASIC, analyzing it to basically any number of energy beams. So between 2 and 8 or 10, whatever you wish, it's just a number of trade-off of cost and power consumption. Here you can see it in more detail. What happens here, you can see that the anode, the cathode, the X-ray is coming, irradiating the cathode. The cathode is a common cathode. It's under pretty high bias. The bias is around 400 volts per millimeter, and this is between 2 and 3 millimeters in order to absorb most of the X-ray. 2 millimeters has better response, but it absorbs only 93 or 94% of 120 kilovolts. And you can see the signal coming from the anodes. Here are the pixels, the anodes. There are no reflectors here. There is no light, so you can shape the anodes to any size and get the resolution from very small anodes. And the signal goes through a charge-sensitive amplifier that gives a certain amplification to the signal, very narrow signal, coming from very high rise time from the CZT or cadmium telluride, which are the best candidates for such a conversion. I'm still okay. And this is going through a shaper that gives something like a Gaussian shape pulse, and it goes through comparators or discriminator that are set to different thresholds. So when the height of the pulse is higher than a threshold, it passes, and the discriminator sends a digital pulse to a counter, and you count 1. So if you have several thresholds, you can know how many photons, X-ray photons, have energy between a low threshold and the threshold above it. So you can calculate it and see it. So you can here it is exemplified with 4 energy beams, but you can put in the electronics up to we have a system, and a preclinical system for animals with 6 energy beams. People have systems with Siemens has a prototype with 2 energy beams only. So you can put any number of energy beams. Medipix 3 has 6 energy beams, 5 or 6 energy beams, I think, and so on. Here you can see a typical 2.5 millimeter thick CZT with the same number of pixels, but these are 500 microns by 500 microns, which is very small for CT, very small. CT gain also resolution from the magnification. So 500 usually magnification is around 2, so 500 mean 250 microns in the isocenter, which is good, even with if we assume that we hit the Nyquist by dynamic focal spot. I have it here, and this is a larger one. Here you can see a pixelated scintillator. Just going back a little bit, I would like to mention that people were talking about, people sometimes talking about photon counting with fast scintillator and electronics, like something like silicon PMs, but with the scintillator conversion, you end up in silicon with about 1,000 electron hole pairs created by a 60 keV photon, X-ray photon. In CZT, you create about 13,000 electron hole pairs. So this affects the energy resolution very much and the signal very much. So if you want energy resolution, you need these direct converters. There is no way to do with CT X-ray energies a good photon counting system with scintillators, although there are trials to do it. A little bit on the photon counting energy weighting versus energy integrated detector. In energy integrated detector, this is a phantom, a mathematical phantom. This is a simulation where this is water, this is muscle taken the elements composing a muscle taken from NIST table, and this is water, and this is a plexiglass. Everybody knows it's not shown very well here because it's not a DICOM image here, but everybody knows that when water is around zero in CT, the Hounsfield unit, a plexiglass is around 100, even 110 PMMA is plexiglass, or lucite, sometimes people call it. And this is very strange because lucite or plexiglass is only 13% more dense than water. The density is about 1.13, 1.15, something like this. But the atomic number of lucite is about 20% smaller than water. It's about 5.6, where water is 6.6. The effective atomic number, I don't want to talk about how you calculate effective atomic number, but there is already Hans Bethes methods to do it, so I can direct you to or you can ask me offline. However, and if we think, well, the signal in energy integrated detector takes in account more the photons with the higher energies. So this is the energy weighting of energy integrating detector. However, photon counting without the energy binning, photon counting is weighting equally all the photons without energy weighting, equally all the photons, and suddenly you can see that the photon counting image here has the PMMA, the lucite, the plexiglass with a lower Hounsfield unit than water, as you expect it to be, because of the effective atomic number. And and not only this, the contrast difference is much higher. So you get much higher contrast difference. However, if you take 8, here I've taken 8 energy beams only of 11 keV each, and I sum it together, but weighted the sum with the weighting of 1 over e to the power of 3. 1 over e to the power of 3, which is approximately energy dependence of a photoelectric effect. So you can see that I don't have the numbers here, but the contrast difference, or the CNR, because the noise is almost the same, the CNR increased relative to to energy integration by 200%, factor of 2, more than factor of 2. Here it's by 40 or 50%. Here it's so the energy weighting enable us to manipulate the analysis of photon counting data such that we can direct it to the tissues that we are interested in, increase the contrast difference or contrast to noise there, and see more information, and increase the sensitivity for contrast agents, for example. Or alternatively, to reduce more the dose. People are talking about dose reduction all the time, and this is dose reduction which is totally independent from the dose reduction that you achieve from iterative reconstruction in CT. So this is an opportunity and very promising feature of photon counting. Now I would like to touch a question that people used to ask me in Philips management, and everybody and some physicians ask, why do we need more than two energies? What do you get from more than two energies? And physicists even in hospital tell me, well, there are only two physics parameters here, the Compton scattering and the photoelectric in this energy range. So two energies are enough to extract them and know all the information. So first of all, there is another, if you have heavy metals, heavy elements, like gold or something, or you have also the K edge, which is a third physics parameters. But even without this, look at this experiment. This is a real experiment. This is not a simulation. This is a phantom, a 7 centimeters phantom with 6 tubes with all kinds of mixtures of iodine, gadolinium, calcium, high and low concentration. This is the H and L, solid carbon, graphite, and also air bubbles in forms here. In order to have all the range of materials, interfaces, and more than two materials in a mixture and in interface. And we scanned it with a mini CT rotating table, benchtop CT that we have, a photon counting one, a very good one in a laboratory in Haifa. And you can see we have taken a two energy analysis, a dual energy analysis, with two separate windows, excellent energy separation, one between 25 and 46 keV, and one between 85 and 125 keV. So they are very well separated, much better than any system, than any commercial system, dual energy system, and still we see that the analysis is very dirty. It separates the material, but with lots of interference between the materials where they should not appear or should not be. Here we use the same data with 6 energy beams, well defined here, and you can see that everything is seen very well, including air bubbles. Am I okay? Yes, I have. I'm close to finish. So this is where we need it, and the question is, if everything is so good, why don't we go to photon counting CT? And the answer is that there are still lots of, where is the catch? The catch is in some basic difficulties, both in the material and in the method itself, that has to be overcome. The main problems are, first of all, pile up. When you increase the rate, so as long as you detect or sample rays that are going through the body, an adult body, even at high tube current, gives the rate at the detector is not that high. But at the edges of the patient, the rate is becoming very high, and we suffer from pile up. I'll show the pile up, but you know that radiation quanta are coming randomly from from a tube, and they are subject to Poisson statistics. So there is a very good chance that two quantas, two photons, X-ray photons, come together to the detector. And this affects the possibility to measure. And the other problems are in the material itself that can go to polarization. So you get accumulation of space charge, especially of holes that are not so fast drifting inside the semiconductor like electrons, especially in CZT and cadmium telluride, and they create a space charge that distorts the field that you get inside, so the drift is stopped, and you get you lose the signal. And there are because of that, you would like to go to very small pixels in order to have only a low rate at each pixels. Even 10 by 10 micron pixels or so. This could be excellent. But there is a trade-off here, because if you go to very small pixel, you get charge sharing between the pixels. You can get drift of charge between the pixels, so it ends up with a low energy tail if you irradiate with a radioactive source, monochromatic source. And there are also K fluorescence escapes from pixel to pixel of tellurium and cadmium, which are around one is 27 and one is 30 keV, the K alpha. One is 27 and one is 24, I think, and keV, and they can, if an event occurs at the edge between or at the boundary between pixels, you can get very easily these escapes of that I'll show. A little bit on the pileup. Here you can see a pileup. The pileup is first a phenomenon of the electronics, and you can see the effect of pileup. You can get in the spectrum events that are higher than the highest energy photons in your spectrum, because events are added together to give you higher energy in the detector. And because of that, if you measure the outcoming rate versus the incoming rate, unlike energy integration, you don't get a linear response, but you get a nonlinear response. I don't want to get into the parallelizable and non-parallelizable. I would like just to show that the DQE is almost 1 at low rate, unlike energy integrated, but it reduces dramatically in high rate. Here you can see a response of very small a response of detector with very small pixels to americium source, about 60 keV source. You expected to get this, and you get all these tails. With 55, this was done in Medipix, this was done in CERN, Karlsruhe with CERN. It's taken from this paper of Koenig et al. And you can see for the 55 micron pixels, you don't get any spectrum. You just get junk. For 110 micron pixels, you get something, but you get lots of escapes. These are the escapes. These are the remains of the escapes, and these are the escapes coming from neighboring pixels. And all the charge sharing is under these shoulders. And this is how you see it also in when you measure a spectrum of a tube, a 110 kilovolt tube. This is the spectrum of the tube. And you can see that only in 165 micron pixels, you can see the bumps of the K alpha and K beta of the tungsten from the tube. So this is a very important thing. A little bit on application. This is the preclinical system that we have in Washington University in St. Louis. In Hamburg we have it. We did some work with Mount Sinai. This is an experiment with Mount Sinai with nanoparticles carrying gold, uptaken by macrophages in plaque in the aorta of a mouse. In the plaque in the aorta of a mouse, and you can see how strong the signal is. And this is similar experiments. I don't have time anymore. Similar experiments in this is an important experiment that we did with bismuth carrying nanoparticles, showing a problem in the iliac artery. This is a zoom of the iliac. Here you see it pretty well in a mouse, in a rat. And this is experiments with nanoparticles with erbium and so on. So in consequences, just in summary, basically over the last 10 years, detection innovation led the evolution and revolution in CT, including the multi-slice revolution. Detector-based spectral CT enables benefits of material analysis for all protocols. You don't have to prepare a specific protocols for dual energy. You can get and retrospective, you can use any protocol and retrospectively analyze it with the spectral analysis. Photon counting looks an opportunity for the future CT, provided that that we can overcome, and we shall overcome this, of course. And there is a race to overcome it, overcome some technology roadblock that I have just mentioned, especially pile-up and tail and low energy tail. Okay, I'm open to questions.